In this BME 3300 lecture, we will continue talking about active filters. Now, last time we talked about low-pass active filters, and today we're going to continue that discussion, first by talking about how you can adjust separately the gain and the cutoff frequencies in active filters, and then we're going to go through some different, some additional active filter topologies, including high-pass filters, bandpass filters, band reject filters, and Butterworth filters. Now last time, to recap, we talked about the active low-pass filter, which I will draw here. So the active low-pass filter has just an input resistor and in the feedback circuit it has both a parallel resistor and a capacitor. We'll call the resistor R2 in the feedback, the capacitor C1 in the feedback, and the input resistor will be called R1. And then, as usual, we defined input and output voltages. Okay, and then the transfer function for this guy can be written as minus R2 over R1 divided by 1 plus j omega R2 times C1. And you can get this transfer function simply by taking the the typical inverting amplifier ratio of the feedback to input resistances equation and plugging in the impedances instead of those resistances, the parallel impedance of C1 and R2 and the input resistance R1. And then you can rearrange that to get this expression. And this is pretty easy to understand how it works intuitively. Essentially what happens is that at low frequencies, the capacitor C1 is an open circuit, right? Because capacitors don't conduct at DC. And so you just have a typical inverting amplifier, and so you can tell then that signals will pass through the amplifier at low frequencies. On the other hand, at high frequencies, C1 is going to become closer and closer to a short circuit. And since you know that the gain of an inverting amplifier is the size of the feedback impedance divided by the input impedance, if you have a short here, that's zero impedance in the numerator there, so you're going to get zero gain at the high frequencies. Now, it's possible to use this filter to simultaneously provide gain and suppress certain frequency ranges, suppress high frequencies, and the gain can be tuned independently of the cutoff frequency by changing R1, the input resistance. And you can see that from this equation, that R1 enters in here only in the equation, whereas R2 and C1 both enter in here where they multiply by omega, and thus their inverse is the cutoff frequency. Now likewise, we can also adjust the cutoff frequency independently of the gain by changing the capacitance, since the capacitance only appears where it multiplies into the frequency omega. And similarly, we can independently change the gain and the feedback of the other active filter, the gain and the cutoff frequency of the other active filters we'll talk about next. So the next topology we'll discuss is the active high-pass filter. Again, we'll define our input as Vn, but now instead of having a capacitor on the feedback network, we're going to have a series capacitor on the input network. And here is V out. So we'll define the feedback resistor now as being RF, the input resistor will be R1, and the input capacitor will be C1. And again, we can analyze this just by taking the ratio of the feedback impedance to the input impedance. And if we do that, and then let's see, I'll write that explicitly here, we take ZF divided by ZI, and if we substitute the series combination of R1 and C1 for the input resistance, for the input impedance, and if we substitute RF for the feedback impedance, and rearrange a little bit, we can arrive at a relatively simple expression, minus RF C1 times j omega divided by 1 plus j omega R1 C1. Now, the passband gain we can get by setting omega equals infinity, right? Since this is a high pass filter, if we set omega to infinity, then we should get what be well within the passband. And so if we do that, then you can see that the one here is going to be negligible, right? Because so this term and this term will dominate, and this one will become negligible. And so then we'll get minus RF divided by R1 as the passband gain, right? Because the C1 and omega and J omega will cancel out. Likewise, the cutoff frequency is given by 1 over R1 C1, right? Which makes sense because those are the two factors multiplying with omega here. Now, just as we talked about before for the low-pass active filter, we can adjust the gain and the cutoff frequency independently. So if we want to change the gain but not the cutoff frequency, we would change RF. Right? So we would change RF if we want to change the gain but not the cutoff frequency, because you can see that the cutoff frequency is independent of RF. Conversely, if we want to change the cutoff frequency and not the gain, then we would change C1, since C1 enters only into this equation but does not enter into the passband gain equation. Now, of course, high-pass filters are going to be used when a signal we want to preserve is going to be of higher frequency than some noise source or other unwanted signal source. Now, in biomedical engineering, since we have mostly low-frequency signals that we're trying to measure off the body, high-pass filters are going to be mostly used to remove very low frequencies, such as DC offsets that we might have on our signals, and drift, that is, slow variations in the signal that vary on the order of seconds or minutes, that are a lot like orders of magnitude slower than the physiological signal that we're trying to measure. So these can be things like changes in the signal due to changes in temperature of the transducer and things like that. Now, many signals will have both low and high frequency noise, right? For example, we might have a DC offset, and we might also have some higher frequency noise from other sources that we've talked about. So a bandpass filter is a kind of filter that can help us attenuate both. Now, the simplest topology that we might have for a bandpass filter simply involves cascading a low-pass filter with a high-pass filter, or vice versa. So in this case, we would have a low-pass filter here first, and then we would separate the two filters with a buffer, and then we would have the high-pass filter on the output. And again, these could be switched. The order of these could be switched. Okay, now the transfer function for this guy is simply going to be the product of the low-pass filter transfer function and the high-pass filter transfer function. So the low-pass filter transfer function is given here, right, and involves the values of R1 and C1, and the high-pass transfer function is going to be given here. On the right. Sorry. Okay, now why do we need the buffer? Well, if we remove the buffer, then the two circuits would couple, and the equations would get a lot more complicated. So what the buffer allows us to do is to multiply the low-pass filter and high-pass filter transfer functions. Now we can also come up with an active bandpass filter that involves an op-amp that has both resistors and capacitors on its input and its feedback. In this way we can get a bandpass filter that also applies gain. There's V in, V out. We'll have R1, C1, and then we'll have the feedback, resistance, incapacitance. Call that R sub F and C sub F. Okay, so again, because this is an inverting amplifier topology, we will have minus Z sub F over z sub n. Both of these quantities are functions of the frequency. And if we substitute the parallel combination of RF and CF for the feedback impedance and the series combination of R1, C1 as the input impedance, and then we do some algebraic manipulations, we can get to the expression j omega RF times C1 divided by 1 plus RF CF j omega times 1 plus R1 C1, and I'm going to have to come down here a little bit, times j omega, close parent. And so here's the frequency response of this filter, whether it's active or passive. So the shape of it is essentially just going to be the product of a low-pass filter and a high-pass filter, right? And so what we'll get is something that looks like this, right? On a log-log plot. So here I've drawn the high-pass filter response component and the low-pass filter response component. The bandpass filter response is the product of the two. Now the cutoff frequencies here are, you're going to have a low-pass cutoff frequency, or sorry, a high-pass cutoff frequency of R1 C1. I'm sorry, that's incorrect. That is, you're going to have a high-pass cutoff frequency of R1 C1, and that guy is going to be slightly less. That guy is going to be less than the high-pass cutoff frequency of 1 over RF CF. Now, I'll note that in this case, all of the components factor into cutoff frequencies here, so it is not possible to independently change the cutoff frequencies and the gain of the filter in this case. There are not sufficient degrees of freedom to do that. So what we have is that at low frequencies, that is frequencies that are less than the high-pass component's cutoff frequency, the high-pass part of the filter is going to dominate the frequency response. Conversely, at high frequencies, where we have frequencies greater than the cutoff of the low-pass filter, the low-pass part of the filter is going to dominate. Now, if the cutoff frequencies are far apart, roughly 100 times apart or so, the midband gain is going to be the ratio RF over R1, and it acts like an inverting amplifier. Okay, so why does 100 times separation matter? Well, that's because if that's so that the midband will be sufficiently well separated from both cutoff frequencies. So we can make a good approximation. Let's say we plot the frequency response on a log-log plot here, and if they're well separated, then we'll have a nice flat part of the response, right, of the magnitude response. This is magnitude of h of j omega log, and this is log omega. On the other hand, as they get closer and closer together, it's easy to appreciate that eventually the rounded edges of the frequency response of the low pass and high pass parts of the frequency response are going to start to interfere. So here I'll draw a case where they might be a little bit too close together, right? So you can see that if you bring them closer and closer together, you're going to start to lose amplitude in the response, and thus you're going to be somewhere under RF over R1. So this brings us to band reject filters, which we're not really going to use at all here. Now, a band reject filter would have a frequency response that would look something like this on a log-log plot. It would essentially pass everything except for this notch here. So you'd have log of h of j omega here, log omega, and then you're going to have the high pass frequency cutoff is now going to be higher than the low pass frequency cutoff, which is the opposite case that we have with the band pass filter. So here's the high pass filter minus 3 dB point, and here's the low pass filter minus 3 dB point. And what these potentially could be used for is to reject a particular frequency where we have a large noise source. On the other hand, though, we need to hope that we have no signal at that frequency so that we're not suppressing signal. So overall, a band reject filter would be justified if you had a single noise source and signal on either side of it, but not at the same frequency. This is going to be really rare in medical applications, really in any application. Furthermore, it's impossible to produce sufficiently narrow stop band without a huge number of cascaded filters. That is, you can't make the notch very tight without a very sophisticated circuit with lots and lots of components. So really, typically the better solution to get rid of 60 Hz noise, which is the main single frequency noise that we're going to have, is to use differential amplification, which will be the topic of the next lecture. Now there's one final type of active filter that we'll talk about, and that is Butterworth filters. And I'm talking about this because it's a very commonly used filter, and it's fairly straightforward to build it, and it has a really nice property that it can get a really sharp cutoff. So to motivate this, I'm going to show you this illustration. So the problem with conventional RC filters, that is resistive and capacitive filters that I've talked about so far, is that it can be tough to get a really sharp transition, even when you start cascading filters together. So here the blue curve is a single RC filter, right? Single low pass filter that we've shown earlier. Then if I take two of those and cascade them together, I get the red curve. If I cascade three, I get the yellow curve. And you can see that while the transition is getting steeper, the roll-off, you're also reducing the cutoff frequency, and the roll-off is not getting any sharper really. This edge, this corner here is not getting any sharper. A better solution to get faster transitions than cascading a bunch of low-pass filters can be the Butterworth filter. And it's a very famous filter. This is the topology, sorry. This is the topology. So we have Vn on one end, as usual. Then we have an input resistance. Then we have the same input resistance, or the same resistance again. Then we have a capacitance shunting to ground. Then we have another capacitor in a feedback loop. And we have the op amp here. There's always an active component in a Butterworth filter. And then we take V out here. So it's a bit different than the topologies we've looked at before. Again, this is R, this is R, this is C, and this is C. So these are the same component values. It's a bit different type of layout than we've seen with the filters we've worked on so far, but it's actually still pretty straightforward to derive the transfer function of this guy. And if you were to do that, you would find that the magnitude of the transfer function looks like this. The magnitude of the transfer function is equal to 1 over square root of 1 plus omega over the cutoff frequency, omega c, raised to the 2n. Okay, so omega c here is equal to 1 over rc, as we've had before, and n here is the number of times you cascade the filter. So it's the number of identical filters with this cutoff frequency omega c that you string together. So unlike a filter with a single capacitor, this one has two, which makes it a two-pole filter. It's what we call a two-pole filter, which is characterized by two capacitors of the same value, and it gives it a sharper transition. So here's an illustration that compares the Butterworth filter when we cascade three Butterworth filters together, comparing that to the conventional RC low-pass filter that I showed you before. So the blue curve here is a single filter for both cases. They look very similar, right? But when we start to cascade multiple Butterworth filters, we actually get a sharper roll-off, and the cutoff frequency does not decrease; it actually increases, and eventually we'll reach a point here. It will just be straight up and down as far as you can see. Okay, so you get a much sharper transition here, and a much flatter passband, it turns out. So you get a flatter passband across a wider range of frequencies. which is good, because really with a low-pass filter we would like a rectangular shape. And we also then get a sharper transition than we do with the other filters. So that marks the end of this lecture. The topics we've discussed are adjusting gain and cutoff frequency in active filters, and omega sub c, the cutoff frequency in active filters. We talked about what components can be changed to adjust those two parameters independently of the other. We talked about four additional active filter topologies. We talked about high-pass active filters, we talked about bandpass filters. We talked about both passive and active filters, although even the passive filter used an active component, the op-amp, to allow us to multiply the two stages together. We talked about band reject filters, which we don't really use in practice in BME. And we ended up talking about Butterworth filters, which can give you a sharper response than conventional low-pass filters with a few added components.